I think I have to make you presenter. Now you are presenter, sir. Now you can share your slide.
Okay, chalo Rajesh. 15 only so far. हैं? ठीक क्या? हाँ हाँ वो दे दूंगा. Hello, Chitrakan sir. Am I audible?
Yes, yes, you are audible.
Hello, sir.
Yeah, you are audible, sir. Audible. Now you can start.
Hello.
Yes. Hello.
Hello, participants. Am I audible?
Yes, you are audible, sir.
Hello.
Am I audible?
Hello, sir. Am I audible?
Yes, you are audible.
Your voice is not coming, sir.
Voice is not coming.
Yes, it is displaying that you are speaking, but it is not coming.
Okay. But
Sir, so please
you are
change
audible.
your mic setting or something connection.
No issue, sir. You are audible.
Okay, I am audible now. No problem.
I think you should start, sir. You should start, I think, sir.
I think now your voice is coming, sir. Am I audible now?
Yes, you're audible. Yeah.
Hello, sir.
Yes, sir. You're audible, sir. You are audible, sir.
So all the participants may also answer about that voice is clear or not.
Yeah,
I
tell
hope my
softly, sir.
voice is clear.
Yes. Some background noise is coming. That's
Sir
why.
is also trying to speak, but I am not listening anything. So, sir, you may yes, yes, sir. Now better. Okay, and I think I am audible now. So I will start that for that today's presentation. So we will discuss about that spice modeling and circuit simulation. I think most of you are uh, from education background, and I think you are either undergraduate or postgraduate. Some might be already in academic institutes. They are teaching or educator, or some might be from industry also. So this is the very basic fundamental session about the spice modeling. Most of you are aware about if you have been gone through that spice modeling and all. So what are the analysis we can do in this spice modeling? So we will start with that. What is that spice? Spice is basically a simulation program with integrated circuit emphasis, and this is actually an environment which will provide that different type of analysis of any circuit, how it will behave in the real time situation when it is being integrated in that any module. And now if we are imposing all such conditions, real time conditions in that in the circuit simulator, and it will simulate that simulate the real time, almost real time, not actual, because we are considering that modeling of the device. Modeling means that there are the different circuit parameters which will vary with respect to different conditions like atmospheric pressure, temperature, and environmental conditions. And there are also effect of parasitics and some circuit uh, other circuit parameters that will affect that performance of device. Ideally, we can also see that ideal situation when we are not applying any modeling, how will device behave. Now if we are providing the model parameters, there are the different levels of model parameters as the technology upgradation has done over the years. That similarly there are the different levels of modeling parameters were introduced. Means that with the technology there are the large number of parameters were introduced in the modeling file, so that will affect that performance. Means either it may be in the positive manner or in that negative manner, because that as you see that always there is a trade-off of power and speed. And now with the scaling in the last session of Chitrakan Sahu sir, that as we are going into that if we are going down in the technology trends, and there are many parameters that will be affected with respect to that technology advancement. So that this basically spice will give an environment that how the circuit will behave in the real time situation, and what are the different types of simulation we can do in this spice software. That is one is bias point calculation. You already studied in your earlier semesters of undergraduate study. And this the DC sweep is that how that circuit voltage or current will be varying with respect to different voltage variation of inputs. And transient analysis, if we are providing that transient inputs, means step input or something that will vary with respect to time. So how with respect to time, how circuit will behave, that is being done by transient analysis. AC sweep and noise analysis, by applying this AC input, that with respect to bandwidth or this time, how the circuit will behave. This is called AC sweep. And there are the secondary sweep. Secondary sweep means if we are uh, this is used to analyze the different voltage variation and the same graphical scale, and parametric variation, temperature variation, and how the circuit will behave in the with respect to various environmental conditions. And last one is that Monte Carlo. Sometimes it is also called worst case analysis. Monte Carlo is the approach that how that in the real time situation, means when at the manufacturing stage with respect to different lots of transistors, there might be variation in the parameters. There are some few parameters like channel concentration, oxide thickness, or threshold voltage variation, capacitance, and there are so many parameters that can be that are having that variation with respect to different lots. So we will be able to analyze the device performance in the worst case scenario. So for that purpose, Monte Carlo analysis is can be done in the spice circuit. However, this analysis is very fundamental, but that a large number of variation in the parameters we will be able to analyze in the circuit. And as far as the research is concerned, there are the many researchers uh, who's done a tremendous research background, has done the research in the by using this tool only. This is the fundamental tool, and this is also uh, one tool that is available license free as well. There are the uh, two versions of that. One is the student version, and second one is that cadence bundle is there, that is the licensed one. So in the cadence bundle, that we will be able to analyze that a large number of variations, a large number of performance analysis, and that parametric variations can be done. And as well as there that some device fabrication or this layout implementation can also be done in this cadence bundle package. And but now as far as this student version is concerned, that is limited up to that performance analysis only. But if you are doing your dissertation or research in undergraduate or postgraduate, even I have done my postdoctoral research in this tool only, because that even in this tool you may explore like anything. So this is a very good tool to explore. So now that how this tool works. So this is we can simulate the circuit by two ways. One is by using that netlist, and another way is by uh, implementing it through the schematic version. So this is like that we can draw that schematic plot, like this is the simple NOR gate, that symmetric this is the symmetric entry, and this is in the data format edif is that version of file. And this can also be converted into the spice netlist text file used for simulation. And there are some pattern of to write that netlist, means that is that sequence of terminals, drain, gate, source, and substrate. That is the sequence of terminal. And what are the applied what is that connection we are making, that node, particular nodes are indicated in the netlist file. And after that introducing in the text file, we simply give that command simulate, and it will provide that the results of our circuitry. Now, what are that different analysis can be done? One is that basic bias point analysis. Like this is a simple uh, NMOS transistor where this is we are applying AC source, and now this single operating point means that quotient point can be calculated by providing that bias point calculation. Similarly, that DC sweep is that one kind of analysis that can be done, means how that with respect to input how that output is varying, means this is that variation of this is the variation of input voltage and how output will decaying with respect to input. So we are providing that variation in the input voltage and how output will behave with respect to input. So this is basically primary sweep, which given in that performance parameters. Now next is transient. Transient means that if that our inputs are varying with respect to time, means time varying inputs. If we are applying like this, these are the sinusoidal or digital clocks are applied to the signal, and how that output will behave as a function of the time. So we will be able to analyze by giving the transient analysis. Secondary, we can also give that AC sweep, means that how output will behave with respect to frequency variation. So by providing that AC sweep, by applying that AC voltage source, we will be able to analyze how that output will behave with respect to frequency variation. Now that key difference between AC sweep and other analysis like transient analysis, DC sweep, and bias point analysis. Like this transient analysis means outputs like this is a simple Smith trigger, as you all are aware that they will be able to convert this basic sinusoidal into the rectangular or square shape pulse. So that output saturates at 10 volt, because here we saturation is 10 volt. So this upper and down waveform levels are saturated at 10 volt. And similarly, like AC sweep, if we are providing AC sweep here, means we will be able to, this transient is basically variation with respect to time, whereas AC sweep means it is basically with respect to frequency. Now, as you all are aware about that, SPICE is the simulation program for integrated circuit emphasis, and PSPICE is a basic SPICE version by Cadence, and it simulates the electronic circuit behavior on computer using that model file of that component, and it makes circuit solving much easier, faster, and accurate. Means by doing simulation, we will be able to analyze that circuit performance in a virtual environment, and we will be able to we can guess that how the circuit will behave in the real time situation when it will be integrated in a module. So this is that these are the steps of installation. That this software is a free demo software and is available at the Cadence websites. And now whichever that I am using is that a 16.6 demo software. However, that upgraded versions are also available on the website. So you can download by clicking the link and install in your directory of choice, and you can start that installation. Now after installation, that how you will be able to create a project, means how your circuit can be made in this environment. So simply you have to click this circuit capture CIS, that is an environment where you have to select this analog or mixed signal analog to digital version, and thereafter you have to create a blank project, and thereafter you have to click on OK there, and this window environment, this window will be there, and this is the working environment where you can uh, simply put your what are the elements that you want to add in the circuits, and if whatever you want to analyze, you can simply draw here. So a blank schematic screen will open, and this is the place we will be able to build the schematic of our circuit. And here a component library is there. Here this library is there, and this are that we are having large number of components like resistors, capacitors, transistors, inductors, and many modules are there, and which can be drawn here, and we can see that circuit. We can do analyze, and we can do the circuit analysis. So notice that that three tabs on the top, click the one with your project name. So you can here like file, you can create the project name. And now that opening the project page demo, you will find a library like, and right click and choose 8 files. So simply these are that few examples. And now this add file, new pop-up window opens up capture folder, and this there's a pspice is that one directory where simply that like this will represent a register, and these are that some commands. And so how you can choose any uh, any device or any module from this library. Now that added library are displayed in the library folder, and you can simply control plus s, you can save your library. Now this part, now you have to, if you want to draw a circuit, you have to choose the parts, like this is the symbol to choose the all the parts, plus you can choose all the parts from here, like capacitor, like a resistor, inductor, voltage source, current source, ground potential, like power supply and all. So this you can simply choose all that circuit elements from this window. Now if we are taking we will I will demonstrate by one example, like simply resistor circuit. This resistor and voltage supply source are chosen from the library, and now that how this will behave. So this command will be for resistor purpose, that simple resistor is there, and by double clicking the value means you can simply double click this, so you can introduce any value, and I will demonstrate in the real time software environment, and you will be able to better analyze that. And simply select VDC, and the VDC is this for this purpose to introduce this voltage supply source, and double click to set that 5 voltage DC. So this is the simple circuit. So now here for making these connections, this wire connection, the place wire, or otherwise there the one command w is there. W is for purpose of wired connection. So you can simply like, there are the two terminals, so simply you may place these wires in between. So next select ground potential. So ground is there, the command GND will represent the ground, and this this is also another command for ground, 0/source when asked for. So this completes out the circuit schematic, and now we will simulate our circuit. So you can analyze that now if we are analyzing it with respect to time, means there the we can do this simulation setting. There the actually this is for the simulation window, so you can create a simulation setting, or you can create simulation profile by clicking this. So what are the analysis, like this is the one time domain, so there are the different DC sweep, AC sweep, noise, Monte Carlo, worst case analysis, parametric. There are the different analysis can be done by this by using this simulation setting. So now we are running that this for that 100,000 nanosecond, and this was the earlier one was the transient analysis. Now if we are doing DC sweep analysis, so we simply give that variation of that voltage source from 0 to 5 volt and additionally we are providing 0.5 voltage increment. So simply we can analyze how the circuit behavior, that so there is a variation of 0 to 5 volt with 0.5 voltage is that uh, we have divided this scale across this from 0 to 5 volt, and how this voltage varying as this is down, because there is that voltage drop across the resistor, so it will drop down. So this is basically there is a run button here. This is the run button. This is for creating simulation profile, and this is for the simulation settings. And you are providing by clicking this, you will be able to simulate. And then these are the current and voltage markers. This is for single-ended terminal. These are for the differential-ended terminals. And this is the current marker, and this is the power marker. And these voltage current are will display that voltage at a different node in the circuit, and this will show that current in different branches, and this power button will show that what are the power dissipation or power drawn from that particular branch. Now another is that DC bias point calculation. So there is the general setting, we can choose bias point general setting, and this is that example, like a simple circuit where we are applying 5 voltage source and DC source, and simply putting 100 ohm resistor. So this is that voltage marker, and these are that current drawn in the circuit 50 microampere, and this is that power dissipation across this resistor, and this is the 50 microampere across the loop. So this is this can be displayed in our environment. Now another circuit is that simple RC circuit. So how this AC sweep and AC noise analysis can be done. Now this AC sweep source, as we are applying that AC source, and there is a variation from 0 to 2.5 volt, and with respect to frequency, how this will vary. So as you can, this is simple RC circuit. So as far as the time is concerned, that voltage, that whole voltage will be stored across this capacitor, but by the time this will be decayed across the resistor. So with respect to frequency, this is that there is exponential decay curve is there, and you can simply calculate time constant as well. As you all are aware, time constant is where that we will be able to see that time constant when that it will decrease that maximum voltage up to that 37%. So this will give that time constant. And another version is the another analysis, which is the transient analysis. Like this is that this is the voltage source which is varying with the time. So how this variation, how this voltage across the capacitor will be there. So this is the simple time domain analysis or transient analysis can be done in this tool. Another one, this is the simple example of half wave rectifier. Like as you all are aware, this is the half wave rectifier, and by applying this, this is that V1, and what is that V out across the resistor, how that output voltage, because as you all are aware, for the positive cycle this transistor will be on, but for negative cycle, for negative cycle it will remain off, and again for positive cycle it will on. So this is the simple circuitry of half wave rectifier, and how you can also analyze that waveform functionality of half wave rectifier. So this is also time domain analysis, because we are doing it across that time. So this is the basic example. So now these are that we have studied about that basic analysis. Another analysis are process variation or Monte Carlo analysis. Monte Carlo is essentially statistical analysis that calculates the response of a circuit when device model parameters are randomly varied between specified tolerance limits. So according to a specified statistical distribution. So for example, all the circuits are encountered so far have been simulated using the fixed component values, as that we are providing the fixed component values for different circuit elements like resistor, capacitors, inductors. But in the real time situation, there might be variation. So because each element is having its tolerance limit, for example, resistor is having tolerance of 1% plus minus 1. So you can expect actual measured resistor value to be somewhere around 9.9K to 10.1K, because it is a tolerance. Like similarly, other components, there might be variation. So this is the basic simple example. Now in that advanced analysis, as we are doing analysis with respect to transistor level circuitry, so there are the many parameters in the transistor that can be varied in the real time situation. So by varying different transistor parameters like oxide thickness, threshold voltage, channel concentration, and so we have to see that real time scenario, and what are the variation in different parameters. So this is also called worst case analysis. Why worst case? Because as I have already discussed this in the first slide, that in the real time situation there might be variation in that manufacturing process of for the different lots. So there might be, of course, there will be variation in the different circuit parameters, different device parameters like oxide thickness, threshold voltage variation, and channel constant. These are only few. So, by doing this Monte Carlo analysis, we will be able to vary all those parameters, and we can see that the worst case scenario. So in the worst case scenario, how device will perform, we will also be able to analyze. So that's why it's called worst case analysis and Monte Carlo analysis. So how Monte Carlo analysis is being done here? These are the few steps actually that we have to. We will also discuss it through by using netlist, and few program we will discuss through the schematic one. So here that histogram will appear. Histogram, why histogram? Because there's the variation, actually variation in the parameters. So there this variation either in that might be distributed uniform, or it might be Gaussian distribution. So, so what is the total variation? So, in the most of the cases, we are actually analyzing across this Gaussian distribution, and we will be able to calculate this mean and 3 sigma variation. Why 3 sigma variation? Because 3 sigma variation will give all the samples values, means all the lot values, 99% of sample values, that how this device will perform if we are varying the maximum number of parameters. So these are the some few steps. This mean, median, mode, deviation. This will be calculated by this p-spice, and these are the some commands. Ymax, least output. All these are some commands, and this, like if we have to analyze that output voltage, this is a particular transistor node value, and so if we have to calculate some drain voltage, so this will be substituted into the netlist command. And how this variation in the model parameters is given as a distribution, like here we are using the Gaussian distribution. There might be different type of deviation, uniform and all, and like such parameters, there might we will be use some basic variation in some few parameters, thickness of oxide, threshold voltage, channel concentration, and junction capacitance. So deviation percentage given can be changed if you find a useful reference. There might be some research papers available in this analysis. I will also give you references. So means how this for the different lots there might be variation, there might be different variation or percentage variation in different parameters, and the lot is the command syntax which allow us to specify the variation in the parameter between different MOS fabricated as part of different lots. As I already discussed that for the different lots of manufacturing of these devices, there might be variation in the parameters. So this load command is there. So this is related to manufacturing process. So this is all about that advanced analysis, Monte Carlo analysis. This is also called worst case analysis. So this is all about our presentation part. Now we will see that demonstration. Chitrakan sir, am I audible? I hope am I audible?
Yes, sir. You are audible, sir. You are audible.
All attendees, am I audible? You may put in the chat box. Okay,
You are
so
audible.
we will see that demonstration of species. So, so I hope this spice environment is visible to you all. Is this visible? You may put in the chat box. Visible. Okay. So, so now that I have created one basic project, blank project. So you can create simply a new one project. Like this is that method I already discussed. Analog or mixed signal ID, like simply demo. Okay, like we have chosen some directory, so now you can give some create a project. Now this is that blank project is created. Now here, as you are able to see, this is that library here. There you can see that place part. So you will be able to see different parts which are available here. Like this is the source, like this is the voltage source that is available. So you can see here, you can put it here. And now if we want to place different discrete element like resistor, like we have discussed, this is given EVAL double A. This is the resistor. Like similarly, there are that capacitor. There are the different capacitors are there. Like this is C break. This is the like as you all are aware, there the different types of capacitors are available. Ceramic one and variable capacitors. Like if we are taking that simple capacitance. So this is the way, and how these are connected. Now so you have to simply click W. So W is means place wire. So you can connect, like we are joining these elements, like we are making the connection. And now as you are aware that this, now if we want to some DC volt, like this we have chosen pulse, yani that transient source. If we want to give some DC voltage source, if we want to introduce DC voltage source, here there the DC voltage. And then if this how we can choose that voltage, this like that we are chosen 5 volt as a voltage source. So this is the simple circuit, and this is the way you can choose that simulation profile. You can create simulation profile. So like you want to do some DC analysis, so DC analysis, create DC analysis. So some window will appear that is called a simulation window. So you here you can choose simulation settings. So as we are applying only DC source, so you can give DC sweep only. So like if we are like this source 1, so you can simply see V1. And if you want to vary voltage 0 to 5 volt, and you can see with respect to increment of 0.5 volt. So this is how this circuit will behave. And so if you want to see that how voltage will vary across the resistor, so you can simply place a voltage marker across the resistor. So this is that a simple circuit we can simulate. So this is that simulation button that is used for that how that circuit will behave. This is the simulation window that how voltage will vary with respect to applied voltage. So this is taking some time. There are some warnings were reported here. Some, I think, simulation running. I think there is some node is floating. I think node is floating means there is some error. Error in connection means that wire is to be, I think these wires are properly connected. I think there might be some problem. I think some of element might be floating. Actually, that error is showing that simulation aborted, because that we will be able to the some all three terminals are connected. It's all that devices. I think these are properly connected. Okay, no problem, no problem. That there might be some issue with this particular circuit. Already made some the basic fundamental circuits that that we will be able to this MOSFET, like this is a simple transistor is there, and we are applying this voltage VDD across this drain terminal, and this is connected with the source, and and voltage means VGS, and so we will be able to analyze. So simply I have already created some simulation profile, and simulation settings are also being done by me. That DC sweep means that we are providing primary sweep of input voltage. Here input is, we are only giving 0 volt. 0 volt means we are giving variation to this uh, uh, gate voltage. So V5, if we are varying all voltage from 0 to 2.5 volt, and with incremental value of zero point 0.1 volt. So how this with how there is a variation of VGS with respect to how this and how this current will vary. So if we are providing this is the current marker, actually current marker. So how ID will vary with respect to VGS. So you can simply simulate this program. So this is simply VGS versus ID. As you all are aware, this is the input characteristic of a transistor. Here VGS is here. This is the VGS cutoff, that is also called V threshold. So normally it is having the typical range of around 0.35 volt to 0.45 volt for the NMOS transistor. So after that VGS cutoff, that current will start that circuit will start conducting, so that the incremental change in drain current. So this is a simple primary sweep or DC sweep. So this is the basic analysis of DC sweep. Now, if we want to see that secondary sweep, this is the only primary sweep. I have also made one circuit like DC analysis. So for that secondary sweep, so this is we are taking the example. Same example means how this circuit will function with respect to different variation in the voltage. This is the VGS and this is the VDS. VGS is V5 and VDS. So we will draw output characteristics, and this is the current marker, and we will plot that voltage versus current with, and there will be the variation of VGS and VDS. So you will create simulation profile from here, and simply that you will be able to change that simulation settings. So here I have changed simulation settings. DC sweep, I have chosen the DC sweep. I have given two sweep variation. One is the primary sweep, second one is the secondary sweep. I have given primary sweep is as a VDS, is that will be plotted across the x-axis. So V6 is varying from 0 to 5 volt with incremental change 0.1 volt. And similarly, now we are drawing output voltage for the different VGS values. So here VGS is secondary, we are plotting in the as a secondary sweep. So V5 is the VGS. So we also varied 0 to 5 volt, and with the incremental change of 0.5 volt. So for the different VGS values, we will be able to analyze how VDS and how drain current will vary with respect to variation in that drain to source supply. So you can simply simulate the program. These are only fundamental examples. I think you have already studied in your uh, previous in the beginning semesters of your undergraduate study. As you all are aware, this is that output characteristics. So this is the variation of VDS, and this is the drain current VDS versus ID, and we will be able to see that different drain current variation with respect to different VGS values. So from 0 to 5 volt of VGS variation for the 0.5 volt incremental change, there are the different plots we will be able to see. And similarly, we have done analysis for the variation from 0 to 5 volt. So this is all about secondary sweep. Now similarly, we will be able to see AC analysis. Whatever we have seen in that our PowerPoint presentation example, I have drawn the same circuit like simple RC circuit. This is the simple RC circuit. We are applying 100 volt AC source. So how this or how this what is the variation across this register? So you can simply see that you can simply put that simulation settings So here we are analyzing AC sweep or noise. So you can choose simply AC sweep here, time domain, DC sweep, AC sweep, bias band. These are the various analysis of type of analysis. So simply you will choose AC sweep, and this is at as you all are aware that at logarithmic scale of frequency, we will be able to see how voltage will vary with respect to frequency. So we are giving variation from 10 hertz to 1 terahertz, 1 gigahertz actually. 1000 megahertz means 1 gigahertz, and we are giving 20 points per decade variation. Now this is the applying, and now we will simulate this program. So you can simply see that how voltage across resistor will vary with respect to frequency. Oh, now this is the plot. This is the plot. From where you can simply see that time constant value, and time constant is given by where that our voltage will drop down up to the 37%, and that will give that RC constant or RC or time constant. So this is the one kind of analysis. So we have already studied DC analysis, and in DC we have done primary sweep and secondary sweep, and in the AC analysis you can see that how there is a variation with respect to frequency. Now another example is for like similarly we will can see that DSC analysis for the basic simple CMOS inverter. Like this is the simple DC. We will analyze that DC sweep the CMOS inverter. So as far as that with respect to input, how that output will change. So we are providing the primary sweep of input voltage source. Here input voltage source is given V4. So we are varying V4 value from 0 to 2 volt with the incremental change of 0.1 volt. And this is the only primary sweep. We are only analyzing primary sweep. So we will provide that voltage input and output. So we will be able to see that how output will vary with respect to input. So there are basically two plots are there. One is input, second one is the output. So as you all are aware, this basic functionality of CMOS inverter. So as far as input is increasing, output will decrease. This is as input is increasing linearly and output will decrease exponentially. So I think you have already studied in your third year or second year of your undergraduate study. This is the basic functionality of CMOS inverter. Now further there is that we'll see the transient analysis. Transient, as we discussed in our PowerPoint presentation slides, that this is that variation of variable inputs with respect to time. So we will be able to analyze that how our circuit will function with respect to time. So for the transient analysis purpose, uh, we have to apply in size source as which is time varying. So this we are using on pulse signal, where this V1 and V2 are that this is the minimum value, this is the maximum value variation, and this is that delay time. 1 nanosecond is the delay time, and this zero point 0.2 nanosecond is that rise time, and this 0.2 is the fall time. As you all are aware, what are the rise time, fall time, pulse width, and the period of pulse. So force is applied, and we will um, provide some simulation setting, and we will select time domain or transient analysis in our general settings. So we will see how that voltage will be varying with respect to time. So we will restrict only up to 160 nanosecond, and we are choosing 10 nanosecond as a step size. So this we will see that how it will function, and we will be able to see input and output voltage. So you can clearly see this is that input voltage M1G, and there is a output voltage. So this is the basic functionality of CMOS inverter. As you can clearly see that with respect to input, how output will vary. So if input is high, you will be able to get output as a low. So this is the basic functionality of CMOS inverter. So we can do transient analysis as well. So are the very basic fundamental analysis we have done in that our spice circuit. So and further that there are the many performance parameter you can evaluate. So from this, like in any inverter or any circuit, you will be able to check that performance delay. As you all are aware, what is the definition of performance delay? It is actually average of time where that pulse is moving from low to high and high to low. So with respect to this is that input M1G, and this is the output. So you can clearly choose cursor point here. So that as you are able to see that from here, this transient analysis has that the minimum value is 0 volt and maximum value is 1.8 volt. So similarly here is the power supply source. So that from 0 to 1.8, that is that maximum attainable value. So simply that how that pulse is achieving 50% uh, value of that maximum voltage. So now you can choose any two consecutive points, and you can zoom out here. So you can simply zoom out one portion of the wave, like. So this is that input, and this is the output. So you can choose that cursor here. So this is the input. So you can, this is that window. As you are able to see, this is the window. Just a minute. So you can see here, like this, there is how this will vary. So now, just a minute. This we are choosing this input. So this M1G is the input. So you can clearly see cursor 1 is indicated indicating input voltage, and this cursor 2 is indicating output voltage. So how this will fall down up to, as you can clearly see, it is falling 1.03 volt input, now 942 millivolt. So it is around this is now in between 849 and 942. It will give a zero point 0.9 volt, because that 1.8 is the maximum value and 0.9 is the 50%. So you will be able to see 55.302 or 55.301. So you can choose any value, 301 or 302. It is the value when input is going down from high to low, and at the same time output is going low to high. So you can clearly analyze this. So you are choosing this output voltage, how this output pulse is varying. So here cursor to M to D is showing that out. This is like this is that zero point 0.9 volt or 901 millivolt. So 55.332. So earlier you chosen I think 301, and this is the 332. So there will be that variation of around 31 nanosecond from when input is going high to low. Similarly, you can choose for when input is going low to high. You will be able to move that cursor by choosing this M1G as the input. So by moving this cursor from here to here, so from if input is going from low to high, and what is that as cursor is moving up to 50% value of 50% of the maximum attainable value, that means zero point 0.9. Here you can clearly see that 1G is increasing, and it is 0.856, and now this is around 0.9 volt. So you can clearly see 61 point 100 nanosecond, and when input is going from low to high, and how output will vary from high to low. So here output pulse is given by M2D or a green cursor. This is around 99. So that is 61.124, and originally it was 61.100 when for input. So there is a delay of around 23 nanosecond. So in earlier case from input, when input is high to low, it was 32 nanosecond, and when input is low to high, it is around 23 nanosecond. So the average will be 31 plus 23, that is I think around 54, and that average propagation delay will be 27 nanosecond. So this is how we will be able to evaluate performance parameters. So this is the one way to analyze. So this is that one of performance parameter you can see. Similarly, you can evaluate power dissipation, output enable time, and other parameters as well. So this is all about all about that basic analysis in the PSpice, and I have done this analysis through schematic version, through by using that schematic analysis. This can also be done by using that netlist. Some of you might be writing the codes in that in this environment, PSpice A to D, and you can simply write here that simulation text file, and simply you can simulate from here. So there are the basically two way to simulate the circuit, and we can analyze that circuit performance. So this is all about that spice modeling and circuit simulation. We are having limitation in the limitations of time, so it is very difficult to complete all advanced analysis in that limits. So Monte Carlo and parametric analysis, if time will permit, we will see in that some subsequent sessions, or otherwise I will give you some and demonstration examples, or how to write the codes for Monte Carlo analysis, and I will give you that reference study materials to do such analysis. So this is all about the today's session. So thank you very much for joining this session. About the next session, Professor Rajesh Saha will continue, and this session will be done through Google Meet, because there is some issue with this WebEx environment which is not having compatibility with Linux environment, and